He is graduated UW Civil Engineering this year, and brought his two teammates for the bridge competition. That's Andrew, who's a senior at UW, and Alex on the end, who is also a senior, both in civil engineering. And they are going to tell us all about their bridge competition, which is kind of cool. I saw them put this together this morning, and they have videos, so it'll be cool. So take it away, guys.
Good morning, everybody. On behalf of myself and my fellow co-chairs, it's great to be here, and we're excited to tell you all about our bridge. So we did just get a little introduction, but yeah, there's me. I'm Andrew, again, fourth year, just up the road in Beaver Dam is where I'm from. Casey, of course, here from Waterloo, and Alex over there from Menominee Falls. So in our presentation today, we'd like to first talk about, well, what is Steel Bridge? Talk a little bit about the two main competitions that we participate in, go over some of the rules of the competition, and list some of our main competitors, both regionally and nationally. Second, we'll move on to the history of Steel Bridge at the University of Wisconsin-Madison. We have some good pictures for you all, and we'll give some past results well over our, 20-year history or so, something like that. And then we'll talk about Madison. That's Madison, the bridge over there from this past year. Talk about our team, go over some of the design issues that we had, talk about fabrication, naming the bridge construction results, and finally the people who supported us, our sponsors. So first starting out, the goal and the competition itself, we are, in the 35-page rule book or so, we're given this lengthy mission and summary of what we're kind of all supposed to follow in this Steel Bridge competition, but basically it's an intercollegiate competition where students are challenged to 1, design, 2, fabricate, and 3, construct the lightest, stiffest, most aesthetically pleasing, and fastest to construct steel bridge, which has to hold 2,500 pounds. So I guess when I tell some of my friends about this competition that I'm involved with, they kind of think, oh, well, you have a competition this weekend, or is it every weekend kind of a deal? But no, we only have 2 main competitions. One, a regional competition, which is usually held early April. This year was at Notre Dame University. And those who place in the top 3 at Notre Dame move on to the national competition, which we had the privilege to this year, which was at the University of Missouri, Kansas City. So now we're going to move on and talk a little bit about some of the rules associated with the design of the bridge.
Yeah, so I'm going to let you know the basics of the rules. So Andrew said it was somewhere around a 35-page rule book, but we're just going to go over the most important ones. So the bridge has to be made out of steel, which is defined in the rule book as an iron alloy that will be attracted to a magnet. And here you have a diagram of the build envelope that we can actually design our bridge to. So on the left we have a profile view, and you can notice that there's a river in the middle that needs extra clearance, so that was a design consideration we had to take into this year. And on the right we have a cross section, which shows you that you can only have a 5-foot tall bridge at the most and 5 foot wide, and it needs to accommodate a vehicle passageway, just like a real bridge would. So it's very important that you abide to these diagrams when designing your bridge. Moving on, where is that? Oh, it's right here. Let's see, we have the members. So the whole bridge has to be constructible, and each one of these pieces is called a member, which needs to be some kind of rigid body. And each member actually has to fit inside this 3 foot by 6 inches tall and 4 inches wide box. So that whole bridge has to fit in this box.
1 piece by 1 piece, not on the
Yeah. So it's very important that that happens. And there's also some construction rules that we have to abide to. So here's a top-down view of the site diagram that we have to build our bridge in. So on the left you can see there's 2 footing areas, and then the bridge goes across there. There's the river in the middle. And this year the rule was the builders can walk anywhere except the river. And the rules kind of change every year, so you have to come up with new ideas. And your members start on the right. There we go. And here's some fun rules this is like less than half the rules, but some of the most important. So we had 6 builders this year, which was the most you can have. We could not use any drills this year. No batteries were allowed. Last year there were. Nuts and bolts can't be put in your mouth. This is a rule because we actually did that 3 years ago, but then they put it in the rules that you can't.
They didn't like it.
So,
Choking hazard or something.
during your actual timed construction, if you drop anything, it's a penalty. It'll be a 15-second penalty added to your score. So it's very bad to drop anything. And the total time has to be less than 45 minutes. We haven't had a problem with this, but it is important to know. What else we got? Oh, we have loading.
Yep. So we do have to load this bridge. Obviously, bridges get loads on them. Basically, like we said, we put 2,500 pounds of steel, and we get 6 different load cases, where each of these L1 and L2 loads vary by about 400 pounds apiece. And then we measure at different points from the right side of the bridge, anywhere from 7 to 11 feet from the right side. So they just basically put a strain gauge on it and check how much it's deflected after we got the full load on there from when they put the preload. So I won't play the YouTube video, but we're going to keep it short here. So all these loads are angle irons, which are 2.5 feet long by 5 inches by 5 inches by 5/8 inches thick, and they weigh about 25 pounds. And we have to put about 100 of them on the bridge. So it's kind of a long, stressful process, but it's a good workout. And then how you win. We have this long, complicated form, actually 2 of them that come together. Basically, they time our construction, and then they multiply that by the number of people to get the number of man minutes we put into the bridge. And then they charge us $50,000 per man minute. And then any penalties that are added onto that. And then second, we have a structural efficiency score, which they weigh our bridge, and we get charged $20,000 per pound. So that's not too bad. And then for every inch of some deflection, so they measure at 3 different points, they sum those up. For every inch of deflection, we get charged $1 million, which is harsh. But last year, we placed 5th with a score of about $5 million. That's a pretty typical style score for us. We've done very well, and as you can see, some of the people we compete against here as well. So that was us. These are some of the schools we compete against. If you recognize your school on here, raise your hand. Got a couple? Sweet. All right. Yeah. Most of these on this side we participate in a regional competition with. So Bradley, Notre Dame, MSOE. A lot of good friends with those schools. And then we get up to the national sides. We've actually competed against MIT for 3 years, and then this year they decided they were too good for it. NJIT, Clemson, a lot of top name, really good schools for civil engineering that we're competing against and doing very well against. Any questions so far? All right, moving on. So
a little bit about the history of Steel Bridge. I've only been with the group for 2 years now, along with Andrew here. Casey's been around before, but it's actually been around for longer than I've been alive. Here's a few pictures here of the teams over the years. The first nationals was in 1992. Before then, it was like a local competition, but it wasn't a national competition. And yep, the University of Wisconsin was there. You can see by the N means that we did make it to nationals. If there isn't an N, that means we don't really know if we made it or we didn't make it. So we don't really know. But, yeah. So the rules have changed significantly over the years. You can see pretty large bridges and different construction styles have been used over the years, and then they keep changing the rules. So the competition is constantly evolving. Moving on to the 2000s. The bridges kind of look more like they do today. 2002, 2003, those were good years. I think in 2002, Madison actually hosted nationals, so that was pretty exciting in the Kohl Center. And then 2010s, see the team is very healthy, looking really big, and moving. This was my first year, 2014 was a good year, and then finally 2015 was this year. So there's a very long, successful history of Steel Bridge at UW-Madison, and I made this table here documenting our performance. So yeah, you can see the years, 1992 all the way to 2014, and then we'll reveal 2015 success later. On the left-hand side is the regionals results, so we're pretty good at regionals. Top 3 in a category gets you a plaque, one of those things. Yeah. So very, very much success here, and then if you get top 3 in the overall category, that means you get to go to nationals. So on the right-hand side, we have our national results. In early 2000s, we were pretty good. Since then, it's not as good, but you're competing, with the best of the best. There's 40 teams roughly there. And here on the bottom right, if you can kind of read this, are the names of our bridges that we know of. We like to name our bridge. So very fun. We like to keep track of that. For now we're going to move on to this year.
Yeah, so first you heard about some of the rules of the competition, our competitors. Second, we moved on to more of the history, which Alex just told you about. So now for the third part of our presentation, we want to move actually on to the 2014-15 season, the Madison Band year. So first we're going to talk a little bit about the team itself, who's all involved with the team. Second, we move on to more of the design of the bridge. Third, fabrication. And then lastly, construction of Madison Band itself. So we have, 35 active team members that come from a variety of different engineering majors. Mostly civil engineers, but also some mechanical, engineering, mechanics, and astronautics. Even a biological systems major was involved on this team this year. If you tally those up, it adds up to 30, but we also have people on the team who are young enough that they're in engineering, but they may not have declared a major yet. So that's why the numbers there don't exactly add up to 35. We also pride ourselves in being very hardworking. We have 4,400 documented hours, but really it's probably more close to 4,500 hours. And all of that hard work leads into the pride of our 18 consecutive appearances at the national competitions. So you see this picture here on the left, that was last year's Christmas card photo. So we like to show that just to see how much the team has grown just since last year. So that's last year's Christmas photo. And here's this year's. So you can see there's a lot more people involved. We do like to think of ourselves as more of a young team. 75% are freshmen through junior. Well, junior's not really young, but you have to consider that on this team we have seniors, we have fifth years, sixth years, and grad students. So 75% in the first 3 years of the college education is what we consider to be a pretty young team. So moving on, we're going to talk a little bit about the second part of Madison Band, the design process of the bridge itself.
So I'm going to stand over here. Thank you. Yeah, so we do a lot of design, a lot of work. Okay, yeah, sorry. So we have to come up with some ideas, some basic general idea of what we're going to do at the beginning of the year. I mean, we don't just automatically think, oh, we're going to do this right away, obviously. The biggest program that we use is called Structural Analysis Program 2000. It's more of a 2D design, not a 3D finite element software. It's just 2D. But it gets most of the work done that we need to. And then we're always constantly running things back to and from the rules, going through our 30-page rule book, figuring out what we can and can't do. And then eventually we'll get into the 3D modeling for AutoCAD. So as we said before, we kept going with a bunch of original ideas. We had our envelopes, which we saw before. We knew we wanted to do 19 feet. And originally we were thinking, oh, hey, we could probably just run a full-size arch all the way from the bottoms of the feet all the way up and get really nice tight arch. But we decided not to do that because unlike this bridge here, which is anchored fairly well at the bottom of the arch, a bridge like this won't be anchored at the end. So when you start putting loads in the center, kind of like this bridge here, the feet start moving out, and then you get a lot more deflection in the center. So this is an idea we actually scrapped right away. Like I said, we do a lot of design and structural analysis program 2000. I assume most of you are familiar with SolidWorks, right? Yeah. That's what I thought. And then also quite a bit of AutoCAD as well. That's where we do most of our dimensioning. And we do a lot of training. So we put in over 500 or 600 hours worth of design time and training time for our team members. And then for our connections, which we model in SolidWorks, we're actually able to fabricate them and test them in our load machines. So told us a lot about how well we were doing, how well we weren't doing, and told us a lot of good fun. We also have some Saturdays where we just go in and we start drawing on the board and figure out basically some things we can and can't do, kind of try and come up with crazy ideas then. Eventually we come up with a final design, which looks a lot like this one, except for a few minor things missing along the top. And we get our kind of preliminary structural analysis score along with the preliminary weight of what we expect for our bridge to be. And then we model that all up with an AutoCAD. We export this into AutoCAD and then fill in all of our members. And voila, we get a bridge. So next up is fabrication.
So yeah, of course, after you design this thing, then you have to build it. So that's kind of a whole other challenge right there. But thankfully, we have some good resources that we can use. Our student shop at the campus allows us to use their mills and lathes and all their equipment to manufacture our connections. But Endress Manufacturing in Waunakee actually allows us a week of time they donate to us for their shop and a professional welder. So we actually do most of our work at Endress Manufacturing over winter break. And then if we need to make any changes, we come back to the campus and we can have, full equipped student shop to make any changes we want or to make our bridge look as good as it does right there. So the biggest thing to fabricate before going to Endress is to make all the connections. So like I said, we get to go to the student shop. There's Andrew on the lathe, and this is Josh using a mill right there. These connections, after being designed, need to be made, and personally I had very little experience before this year, so it was a learning process for us, but thankfully the staff at the student shop was very knowledgeable and they helped us make all these connections that we want. And these connections you can actually see on the bridge if you want to take a look later, but we wanted to use as much ease of construction type of connections as possible. That means sliding together, which the rules allowed for this year, so T-slots are very fast to construct and they're very strong, so we use those. Gusset plates and sleeves, we also use sleeves, slide together very fast, moment resisting, and single shear connections for easy construction. And we had to make all these in the student shop, and here's just a quick picture of, this is kind of like the halfway point where we have all the connections laid out, but you can see there's no holes drilled in these T-slots still need to be cut to size, so it was a long process. We spent countless hours in the student shop making all these on the mill. But then we take all these connections over to Endress Manufacturing, and our steel gets ordered to Endress Manufacturing. And we also take our AutoCAD drawings over to Endress, and we print them one-to-one, so it's very easy to build our bridge. We just cut the pieces and lay it out on a piece of paper. And then our professional welder, Brad Rick right there, connects everything for us. And after about 1 week, we have a really nice looking bridge. I don't know how it happens, but there it is. And, it's magic. It's just magic. This all takes place over winter break because everyone has a lot of free time, hopefully, maybe, I don't know. But after that, we come back to the campus, spring semester begins, and if we need to make any changes, if we load the bridge, we don't like how it looks, we might change something, that has to happen at the student shop, which they allow us a welding tent. There's KC Welding right there. We actually did have to make some modifications ourselves, and here's our Madison logo that you can see on the middle of the bridge. Looks very nice. We made that using a sandblaster and painted over it. So a lot of stuff happens after Endress Manufacturing as well.
So my favorite part of the year is actually naming our bridge, and I think you guys might get a kick out of this. We named it Madison, but we had a number of other very good contenders, including Bridget, Taking Care of Bridgeness, the Bridge Lebowski, Iggy Celia, Span Wars, Girder, She Broke, Big Bridge Theory. Yeah, we have a lot of fun. We come up with a lot of fun names. If you guys have any suggestions for us, we're always open to hear more. So see us afterwards. Now we're going to talk about the instructions.
Yeah, so you've heard about first the team, Madison, then the design of the bridge, then the creation of it and fabrication. So the last big part of this year's steel bridge is obviously the construction. So my first involvement with steel bridge was last year. I did a lot on the construction team, so that's kind of my forte and where I felt I could contribute most as co-chair this year. So throughout the spring semester, from February through May, we have multiple construction practices. This graph doesn't quite go until 40, but we probably have over 40 construction practices where we practice, obviously, constructing the bridge. The first few are a little rough. They're over 30 minutes, over half an hour. So it takes pretty long to build the bridge, but slowly over time you can see on the graph that, and there's different little breakthroughs, and we get better and faster. We decide to go from 5 people here and add a 6th man, and we improve our time a little bit. So all in all, we start out again over half an hour, get it down to about 6:47 for the regional competition. And then finally at nationals, we have our team record at 4 minutes and 12 seconds.
We're putting together that bridge. It's awesome.
Yeah. So be excited, we'll show the video. Oh, it's all laid out. Yeah, so here's the, I guess the construction site. He just asked about all of the members and stuff. We're all laid out in this staging yard over here, as well as our nuts and bolts and any tools that we have. You saw this picture a little earlier, so we have to figure out how we're going to use this map in this area to construct the bridge. Clearly the river is a bit of an impediment and nobody can walk in the river itself, so we have to somehow figure out how we're going to span over the river. And what we figured out to do is, well, based on the rules, we can actually build the bridge backwards. as we did, and then we can swing it into place, so long as at least 1 foot of constructed portion stays in the footing area. So again, we built it backwards and then swung it in place over the river. And then just to give you a little bit of an outline of that whole construction process, we start here in the beginning. All of our members and nuts and bolts are laid out in the order that we need them to be. We run out, we start the deck, eventually complete the deck, begin the overhead, and then do any final tightening with wrenches on all of the nuts and bolts that we have on the bridge. And then finally on the right there, the finish after it's been twisted in place over the river that you can kind of see taped off right here in the middle. So this is pretty exciting. Next we have the actual Nationals construction run, which we left to play for you here and give a little bit of analysis of how we go through it. So this is the beginning here, just before the start of the stopwatch. Again, all of the nuts are laid down in the nuts and bolts area.
And right about now, our heart rate's going about 160 because this is like our last chance to prove ourselves.
You only get 1 shot. So.
You can see how fast they picked up everything up. That's because we lay out all of our nuts in nice lines so that they can pick them up really fast. All of the members are in a special order so that when we start, everybody knows what piece they're grabbing right away. You can bring it up to the footing area.
Oh, there we go. That's good hide down. All right, so we're still running stuff out. One of the big problems we had an issue with this year was this floor was extremely slippery concrete, so there's a couple times where people were coming into either the bridge or back into the staging yard, and they should about either impale themselves on something or just slip and fall on their face. And it was kind of funny, but also nerve-wracking at the same time. Like, we wanted to do really well.
Again, when we talked about fabrication, we said we designed this bridge so that all of these connections here on the deck and the vertical ties are just going to be easy to fasten together. And you can see how all of these pieces just go together real quick if they slide them right in. There'll be a good example once more. The decks come out here of how those T-slots slide together really easily, but you can see it's just kind of one and done right away.
Bring it in. Got to touch there.
Now here comes the deck here, and they just slide those T-slots.
And you can't hear it, but it's a very exciting atmosphere right now, and there's simultaneously going on like 4 or 5 other runs, and people are all yelling and stuff, so it's pretty exciting.
Yeah. There was a number of other schools that were watching us because when we started talking a little bit of our construction time, they were kind of impressed that we were even under 10 minutes to begin with. But one of the things we pride ourselves on being really good, which gives us a lot of attention when we start doing our runs and our loadings and all that. So one of the other nice things is that we were able to weld all of our bolts in to our all of our connections. So that's typically not, that's a very unusual rule this year that we're allowed to do that. But that meant that all we had to do is have nuts with us at any time. All of our bolts, no matter what, whether they're shoulder bolts or any other kind of bolts, were all 8mm, 1 1/4 by 20. And yeah, so it was really, really easy, really simple, no issues with mixing anything up.
So here you can see the bridge has been constructed backwards from the footing area, and based on the rules, we can set the bridge on Jackson's feet down here. He's supporting the other half of the bridge outside the footing area.
And now we're throwing together the overhead really quickly, so that's these pieces right here, and they just slip in, rotate, and then just nut them on about 10 seconds a piece or less. We also spend a lot of time trying to kill dead time. So if you watch, you'll notice that there's no one really ever standing around waiting for a piece. No one, if they're waiting at all, they're got a hand in their pouch trying to get another nut so they can find something else to nut it up or tighten it up or something like that. So now we're getting the top of the last cross braces in for lateral support across the top. And all the pieces are out, so that all that's left is just tightening.
By comparison, the year before this, it took us 10 minutes to put together the bridge, and it was similar design, but different connections. So, lots of improvement this year.
Final tightening. People should be getting out the wrenches here pretty quick. I think this is about 3.5 minutes.
Yep. Got a couple of ties still coming off the other. Or no, it's already done. So then Bryce is going to have to get out of the middle of the bridge, and he's going to be running out. And then Jackson's pretty much the only person waiting, but he's already picking up and getting ready to swing the bridge around. And then Bryce is
We're
out.
all screaming at them at this moment.
Yeah, so this is about 4 minutes right here, and we're trying to push for a record. Anna and Sarah run around the back, they pick up the bridge. They run around the far side of the river without stepping on the tape, swinging into the other footings. And then as he comes back, Jackson just has a nice little mishap coming in.
That's it.
And that was a personal record for us of 4 minutes and 12 seconds. So. That's mostly Andrew's work there.
Yeah. So being a coach here means you have to make a lot of critical decisions, like way too many. But following our regional competition, we looked at the photos during the load test, and we noticed that there was severe buckling going on at this connection. You can see in the middle picture, this red line represents, the axis and of the two members. Yeah, it's supposed to be straight, it's not straight. So we decided to add this outrigger bracing across this connection, hopefully eliminate this buckling issue. But not everything worked out with that. When we actually welded that member, it bent these overhead just enough so that we were no longer clearing the vehicle passageway. And so that was a penalty, $1 million to be exact.
Yeah, 1/16 of an inch.
1/16 of an inch, and yeah, so that happened immediately following the video you just saw.
So it was like Taco Kong bottom of the valley heartbreak.
Yeah, it was very disappointing. Even with this penalty, though, we were pretty darn successful. So here's the results. Regionals at Notre Dame, we pretty much swept the competition. We just got a second place in stiffness because someone brought a 200-pound bridge, and it doesn't deflect at all. So.
They're only going for that category.
Yeah, but you can see all these if you want later up here. At the national level, we got third place in display, which means our bridge looked really awesome. Second in speed, which you just got to see, that 412 run. 14th officially in lightness because the penalty was a weight penalty, 50 pounds added to your bridge, and our bridge only weighs 93 pounds. So it would have been a second place without the penalty. Stiffness, 6th place. Economy, 3rd place, and that's your construction score. Efficiency, 2nd place if we didn't have a penalty, but the weight made that 11th. And then overall, 8th place, but first without the penalty. So yeah, it was a little heartbreaking, but
We would have beat Florida by about $8,500 if we hadn't got.
here's the final results up here. So we finished at 8th at $5,052,000. First place was $4,064,000. So would have had it. Final stats, 93 pounds. It's very light, deflected an inch, less than an inch aggregate, and that, remember, that's measured across 3 points, so at any given point it's about 1/3 of an inch deflection. And you got to see the construction run 412. And now we're going to move on to the future.
Yeah, there's still next year though, where we'll continue our search for the elusive national title. We elected these 3 guys here, Josh Milligan, Andrew Tesh, and Eric Silvas, to lead our team next year. And hopefully, provided that we place in the top 3 at regionals again in early April, we'll compete at the national level at BYU in late May.
And so finally, we can't do all this work without the help of our sponsors. We've got a number of very good sponsors that we wear on our shirts. If you want to wonder what the shirts look like, Dad's right in the back there. They're not on Dexter, I'm sorry. The biggest contributor that we've had for the last decade has definitely been Engine Manufacturing. Brad, Rick, and then Mike Bush. They've helped us out for a number of years being our professional welders, and they're very, very skilled at what they do. And they're far above the $350 donation to be our best sponsors. Strand Associates also helps out us very generously, as well as AECOM, the American Institute of Steel Construction, and then some of you probably know Sub-Zero Wolf. And then finally, a couple of surveying companies do some nice donations for us. Then we have a lot of individual sponsors. These are people who really supported the program over the years, mostly alumni, but also Mr. D'Arno. He contributes very heavily as the alumni of the program. He understands what steel bridge means for a lot of practical experience as we go into civil engineering. We also have a number of other past team members and family members who've donated over the years, and this really helps us get to our competitions, order all of our parts, and have all of our time. So With that, we are the UW Steel Bridge team. We want to say thank you for letting us come in and present to you guys. And if you have any questions, feel free. Yeah.
So you talked a little bit about the definition of steel. I guess how much time do you guys put into selecting the actual alloy and the materials that